Hello. Here we'll look at examples of running the algorithm for finding inverses. Let's start with a particularly easy case. It will be 3 by 3, but it will be mostly zeros. This matrix came as an adjacency matrix of a graph which is just a loop of length 3, an ordered one. So we're interested in finding its inverse. Algorithm says that we should extend our 3 by 3 matrix by another 3 by 3 by the identity matrix of that size, and do elimination algorithm, Gauss transformation algorithm, transforming the first half into the reduced row echelon form. And since we already have effectively pivotal structure in the matrix, we just need to rearrange the rows to make it look like the identity matrix. So what we can do, we can put this one in the pivot position, in the first pivot position, by doing the row swap between the first and the second row. But now we have rows of length 6, and we have to do the transformations of these long rows. Changing the order in the first and second row will give this, and the last row will be still the same. Now we have our first pivot in the right place. This is going to be our second pivot. Again, we can place it correctly by swapping row 2 and row 3. That will be this row, extended row, and then, oops, I'm making it wrong, 0, 0, and 1 at the very end. My apologies. And then this row number 2 now is going to be the last row. So that is it. We already reached the termination point of our algorithm. The first half of the extended matrix is identity. Then that is going to be our inverse. And in retrospect, is not that surprising. So the computations we did when we saw it as the adjacency matrix of a loop, of a graph, was telling us that that is nothing but the square of that matrix. And then the cube of the matrix is the identity. So the product of A in its square is the identity, making A square the inverse. Let's look at a more interesting example. Again, size 3. So this time we will have zeros on the diagonal, ones everywhere else. And that was one of the examples coming from graphs, but the same question. Is it invertible? And if it is, what is its inverse? Let's compute it. Following the algorithm, we extended by the identity matrix of size 3 and start doing Gauss transformations. The first transformation is to create the pivot in the first position, and we can just do it by swapping row 1 and row 2. Row 3 stays in its place. Then we have to clean up the first column, eliminate this entry. So that is doable by row subtraction. Row 3 minus row 1 will do it for us. Only row 3 is changing in the process, so I'm copying quickly other two. Subtracting, I'll make 0 here. It will still be 1 here, and there will be -1 in this position, coming from the entries in here and the original 1 and 0. In the extended part, I will have 0, -1, and 1 because of that subtracted from the last row. So I've created my first pivot. It sits above zeros. Second pivot is already in its place. I can just start eliminating below it. Again, row 3 will be transformed by row 2 now through the subtraction, getting rid of this entry. The rest of the matrix doesn't change, so we'll have 2 zeros as expected, and then we'll have 1, 1 subtracted from 1, -1 will make it -2 here, and in the rest of the row we'll have -1, -1, and then 1. Halfway through, we are now, we just need to scale this down to 1 by dividing by -12. Sorry, multiplying by -12 row 3, dividing by -2. Multiplying by -12, these entries will give us half, another half, and then -1/2. Now we can eliminate upwards, reducing this row echelon form, doing 2 transformations at once, getting rid of this one and this one. In the first row, it is row 1 minus row 3, which will do it for us. In the second row, it's the same, row 2, just without row 3 will be what we want. And what we want is just the identity matrix, which is the reduced row echelon form of invertible square matrix. What will happen in the rest is what will give us the answer. The last row is not changing, but the rest will be subtracted from the second. 1 without a half will give us a half here. 0 without a half will be -half. And 0 without -half will be just a half. And the same above, the same in the first row. 0 without a half is -half. 1 without a half is +half. 0 without -half is again +half. So that is our inverse. We see the common denominator 2. We can take it as a scalar multiple, put it as a scalar in front of the matrix. Then the matrix will be -1, 1, 1, first row, second row, and the last one. It looks very similar to what we start with, to the original A, but it is as if we subtracted the identity matrix from A. The identity matrix will have 1s on the diagonal, 0s everywhere else. So away from the diagonal, the matrix will not change. On the diagonal, we will change 0s to -1s. That is the answer for the inverse. It's half A minus the identity. Again, in retrospect, it is not surprising because what A was B without the identity, where B was all 1 matrix. I'm recalling the computations we did when we looked at it as a adjacency matrix of a graph. And this all 1 matrix satisfies an easy equation. Squared, it is proportional to itself with the coefficient 3. Doesn't matter whether we compute the product entry, it's all the same because we take the same row, multiply with the same column. The answer is 3 everywhere. So that is the answer for the square of B. A is just the difference of B and the identity. So when we compute its square. I'm recalling the computation we did then. We can use, in this case, a binomial formula as for the same way, in the same form as for numbers, because two matrices are in the binomial commuting. So the answer will be b squared minus 2b plus the identity. B squared is 3b. Without two copies of b, will be just one copy of b plus the identity. If we want to bring it back to a, we have to write it as b minus the identity plus twice the identity, for b minus the identity being a. So that is a polynomial equation which is satisfied by a. A squared is itself plus twice the identity. Well, if we look at it in the different way, if we write it as a squared minus a, putting this on the left side, being twice the identity, and then halving through this equation, 1/2 a squared minus a being the identity. Now we could see the answer for the inverse, so we could check that this is the correct answer, because that we can factor as a times 1/2 a minus the identity. That making 1/2 a minus the identity the inverse of a. Again, it doesn't matter which order we factorize, factors commute, the answer will be the same. So that is, of course, not always possible. It's a special feature of our matrix that satisfies an easy polynomial equation, but when it does, we can always use this trick, writing the polynomial equation in the form a times something equals multiple or just the identity, then that something must be the inverse. That is it for now. See you later.